everyone, or good afternoon. This meeting is recorded. So thank you for joining and welcome to our GODEEEP webinar series. Perfect, thank you. GODEEEP stands for Grid Operations, Decarbonization, Environmental Energy and Equity Platform. This is a PNNL internal investment that aims to provide documented and vetted end-to-end analytics from climate to grid. Specifically, we address the transitions to net zero economies, the associated transition of the electricity sector, and its evolving sensitivity to climate, while exploring opportunities associated with climate services. Finally, we also address the impact of decarbonization of the power grid on communities towards supporting successful transitions for all. This is a recurring series. The kickoff was on June 12th, and we presented the overall platform. Deep dives, like today, are expected to be technical and present in more details our specific component of the end-to-end analytics were developed, and we demonstrate application. We thrive for questions and feedbacks, since one of the emphasis of this project is to make sure that others can use it and can build on what we did. For example, on June 26th, we presented on the decarbonization scenario, as well as the electrification of sectors through the lenses of load modeling. On July 14, we presented on the projection of the power on the grid infrastructure, and all of those webinars are available on godeep.pnl.gov. And today, this is my pleasure to introduce the Deep Dive Seminar 3 on the renewable generations with associated risk and opportunities to the power grid operation. My name is Nathalie Boyzin. I'm a co-PI of GODEEEP, and I am your host today. And let me introduce our expert speakers. First, Dr. Cameron Bracken is an earth scientist in PNNL Earth System Predictability and Resiliency Group, where he has worked since 2022. He holds a master and a PhD in civil engineering from the University of Colorado, Boulder. Prior to joining PNNL, Cameron worked as flow forecaster for the Bonneville Power Administration and also for the Northwest River Forecast Center. At PNNL, Cameron contributes to projects combining water resources, extreme events, forecasting, and hydropower. And specifically in GODEEEP, Cameron leads the exploration of critical energy droughts across renewable, including hydropower, for application to resource adequacy and reliability studies. We're also going to hear from Dr. Casey Burleson, who is an earth scientist in PNNL Atmospheric Science and Global Change Division, where he has worked since 2014. He has a bachelor in meteorology and a PhD in atmospheric sciences from North Carolina State University and a master from Columbia University. A meteorologist by training, Casey works on a broad range of topics, including simulating climate impacts on energy systems. He led the development of the load model called TEL, which you heard about in Deep Dive 1. He's an advocate for open science, which is critically important for tackling today's most pressing scientific challenges. And Casey is the PI for MSD Live, a collaborative open science platform for the multi-sector dynamic community in the Department of Energy. Last but not least, Alison Campbell is a power system data scientist in grid resilience team, where she has worked since 2019. She has a bachelor and a master in astrophysics, a master in energy policy and technology from Cal Poly Humboldt, and she's working toward a PhD in Bayesian methods for energy forecasting at the University of North Carolina at Charlotte. Alison projects focus on integrating variable renewable energy resources into the grid through improved estimation of uncertainty. This shows up in intra-hour reserves to balance forecast errors, day-ahead forecast, and resource adequacy. Alison led the development of the wind and solar renewable power time series presented today, and she's also the co-PI for the Wind Energy Technology Office National Wind Power Database. The presentation will go for a full hour today. We do have Q&A at some natural breaks, and then a longer Q&A at the very end. Please feel free to put the question in the chat so that the non-speaking presenter can address some of the questions on the spot, but we also address them verbally in the Q&A. So without further ado, Cameron, take it away.
Next slide, please. All right. I want to thank everyone again for being here today, and I'm just going to go ahead and kick off this webinar on the vulnerability of the decarbonized grid to energy droughts and climate extremes. Next slide, please. So just reiterating what Natalie said about the GODEEEP project, GODEEEP stands for the Grid Operations Decarbonization Environmental and Energy Equity Platform. This is an internally funded PNNL project that brings together experts from multiple disciplines, including atmospheric scientists, hydrologists, electrical engineers, social scientists, and software engineers. The goal is to build tools, methods, and data sets that focus on grid resilience and reliability, particularly infrastructure and operations that are responsive to climate change. And we're also looking at decarbonization pathways. All of this is done under an umbrella of environmental and energy equity. Next slide, please. All right, in the last two deep dives, we saw lots of good information about what's highlighted in yellow here. In the first deep dive, we heard about the economics and energy demand component. In the second deep dive, we heard about new infrastructure, power grid operations, and the environmental and energy equity component. Next slide, please. Today's focus is going to be primarily on the development of renewable time series and power grid impacts. Next slide, please. All right, so first of all, we're going to start off with some motivation on the sensitivity of the evolving power grid to wind and solar, particularly what scales matter the most. And then we'll talk about the actual development and approach for evaluation of the wind and solar data sets. And the first primary application of these data sets to historical energy droughts across the US. And then we'll talk about some further applications, including energy droughts for storage and market design and extreme events for reliability studies. And we'll end with where we're going to take this work in the next few months. Next slide, please. So as everyone in this webinar probably already knows, decarbonization of the grid is going to require a substantial build out of wind and solar infrastructure. These are results from Deep Dive 2, 2035 projected wind and solar plant sites. On the left, we have the net zero, and the right, business as usual, two scenarios we're looking at. Next slide, please. Integrating all these renewables is going to present some unique operational challenges, and in fact already is. For example, in California, there's something called the duck curve, which is due to the natural diurnal cycle of solar coming on and off, which causes other resources to have to ramp down and ramp up pretty heavily during these shoulder hours. Another example in the Pacific Northwest, where there's lots of hydro in conjunction with wind. In some situations, wind has to be curtailed in periods of high hydro, and in other situations, hydro may have to back down if there's not a market for that energy. Next slide, please. This is all to motivate the scale at which we're going to be looking at today, which is the balancing authority scale. BAs are really the most grid relevant scale. In particular, wind and solar within these balancing authorities are typically must-take resources, and also typically non-dispatchable unless they're paired with storage. Within a BA, if there's a shortfall of wind and solar, this may be taken up this may be overcome through through imports from other neighboring BAs, but only if existing transmission already exists. And then in situations where wind and solar are greater than the load within a BA, this can lead to curtailments if there's not a market. And each of these BAs presents unique integration challenges, specifically due to the regional load differences and the renewable profiles. Next slide, please. All right, in order to model things at a balancing authority scale, we first have to model things at a plant scale. So as of 2020, there were 4,000 solar plants and about 2,000 wind plants across the continental United States with 69 balancing authorities. An assessment of the actual grid impacts requires a long historical baseline, which is unique to each power plant. And I'm going to pass it off now to my colleague Allison, who's going to talk about the development of those time series.
Thanks, Cameron. Next slide. Right, so we need these long historical baselines of renewable power generation. In GODEEEP, we produced wind and solar power time series for a 40-year baseline from 1980 to 2000 based on a single weather simulation. This means that the power time series are developed from both coincident and consistent weather. The first step in the development of this data set, which I'll talk about today, is the creation of a roughly 10-year historical baseline of historical power plant configurations. This allows us to evaluate the process of creating the data by comparing with observed generation. Step 2 is development of a 40-year historical baseline based on power plant configurations in 2020 for use in the energy drought benchmark that Cameron's going to discuss later. The weather data set, which I've shown here briefly on the bottom, labeled as TGW, the weather data set that all of this is based on is called the Thermodynamic Global Warming WRF dataset, or TGW. These data cover 40 years of historical weather, and they've also been run forward in time with a suite of global circulation models that allows us to look at the impact of climate change. So that means that using this same underlying WRF simulation, this TGW dataset, that means that the weather physics of our analysis are, again, both coincident for load, wind, and solar, and consistent between historical and future time periods. This allows us to develop 40 years of future climate hourly time series with future infrastructure to look at the evolution of energy droughts. Next slide, please. I'm going to talk about how we develop the data set, how it is unique from existing data sets, and how we evaluated it for use in analyses of energy droughts. Next, please. First, I want to give a brief introduction into how power time series are simulated. There are two core inputs. You need plant configurations, such as wind power curves, which convert wind speeds into power, hub heights, and PV panel orientation. And you also need a meteorological time series. In the development of these power data sets, we used the exact power plant system configurations. We drew from publicly available wind and solar metadata, such as the EIA 860 inventory, which is shown on the left here. We also used a database called windturbinemodels.com, which provides power curves. And we used the US wind turbine database for wind plant layouts. The meteorological input is based on that TGW dataset for the time period of 1980 to 2020. These two inputs are then fed into NREL's REV model, which is an extension of the system advisor model. And then that produces power time series capacity factors, which means a value from 0 to 1 at each power plant in the United States. So now let's walk through how we create these power time series for each resource. First, we'll do wind and then solar. Next slide, please. The wind weather inputs were extracted from the TGW WRF dataset at each wind power plant location in the United States. To develop power time series, the REV model needs at minimum wind speed, wind direction, temperature, and pressure at least 1 hour resolution. So TGW has these values at 3 hour resolution, so we interpolated them to hourly. We then, to post-process, vertically integrated these parameters to the hub heights of all US power plant locations. Next slide, please. There are a lot of wind plant configurations that are needed to produce a power time series within REV. We need the system capacity, the power curve of the dominant turbine type. And by the way, if you're following along, that is listed, these are listed in the column on the left. So I'm going through those. The turbine layout within the power plant, the hub height of the dominant turbine type, and the rotor diameter. Most of these parameters can be found in the EIA database. And if you want to look for them, they will be in the wind spreadsheet for a given year. The power curves can be found on the wind turbine models webpage. That's a screenshot of that is on the top right. Most of the turbines were available, and for those that weren't available, we synthesized power curves based on all available existing power curves. The turbine layout can be found on the US wind turbine database, and that's shown in the image on the bottom right. You can see that these turbines in blue have a very specific layout that is typically along the ridges of the mountains. There were a handful of power plants that did not have enough information about turbine layout. And so for those, we developed default turbine layouts based on literature. Next slide, please. For the solar power time series, we extracted the wind speed, the surface pressure, temperature, and global horizontal irradiance from the TGW dataset at each solar power plant location. Within most meteorological models, global horizontal irradiance, or GHI, is called downward shortwave flux. So that's why the variable listed there is SW down. To convert into power, REV needs 2 types of solar resource inputs out of a possible 3. These 3 are GHI, or global horizontal irradiance, direct normal irradiance, and global diffuse. Of these, we have GHI, and DNI, or direct normal, can be estimated from empirical models that are based on GHI as an input. So we estimated DNI using what's called the DISC model. If you're curious to know more about these empirical models, I have a link in the bottom that describes this model and links to others. And the DISC model is from the NREL team. So then we prepared these variables for input into REV for each US solar power plant location. Next slide, please. Thanks. The solar plant configurations that are necessary are system capacity, the PV array type, which can mean whether it's fixed or tracking, the tilt angle, and if it's unprovided, then we default to the latitude because that's pretty typical. The module type, so PV arrays can be either thin film or what's called a standard. And then the azimuth angle, which means whether it's pointing due south or west or east. For those that were not specified, we point them due south. If you were in the southern hemisphere, you would point them due north as default. All of these parameters are publicly available in the solar spreadsheet for the EIA 860 database. We also bias corrected the solar power time series using the National Solar Radiation Database as converted to power. We did this using quantile mapping. In post-production, we see that this matches quite well with the National Solar Radiation Database in power units now. Next slide, please. After conversion to power, we evaluated the data sets at the balancing authority level using the reported hourly production for wind and solar as reported from balancing authorities. There are only a handful of balancing authorities in the US that self-report their power production at least hourly resolution. For wind, these balancing authorities are ERCOT, ISO New England, Southwest Power Pool, CAISO, BPA, Mid-Continent ISO, and New York ISO. But you can see here that the baseline is not consistent. Some of the most longest spanning baselines are for BPA and ERCOT. But again, you know, this infrastructure rollout is only over the last 10-ish years. The solar baseline available is much less, but there is data available from ERCOT, ISO New England, Southwest Power Pool, and CAISO. These data sets are the best resources we have for evaluating the development of synthetic power production because they are the actual values produced in each hour. In this evaluation, the capacity factor time series that are the output of REV were converted into actual power production to follow the infrastructure rollout in each balancing authority. This is the first evaluation of wind and solar time series, which has reproduced the actual balancing authority level infrastructure over time. In this evaluation, we looked at the interannual variability given the change in infrastructure over time using the mean annual relative difference. We also looked at the seasonality of the power production through the mean monthly relative difference. Finally, to support our analyses on energy droughts, we evaluated the intermittency of wind and the diurnal cycle of solar using what's called the Earth Movers Distance metric. It's also called the Wasserstein metric, but here I'm going to refer to it as Earth Movers Distance, or EMD. This metric is the difference between two distributions. When we apply it here, it's a measure of the daily time and magnitude difference between our hourly time series. Next slide, please. For the, I think that's the previous slide. Yeah, can we move forward? Thank you, and one more. Thanks. For the evaluation of the wind historical time series, let's start with the left. We find that for the annual energy, when we follow the infrastructure rollout, the average across all balancing authorities is roughly 7% overestimated. But some balancing authorities are better than others. For example, in BPA, which I've shown on the left here, the annual average difference is -2%, so underestimation, averaged over all years. The comparison here is with the self-reported wind production in BPA. In this plot on the left, the BPA reported production is in green, our simulated production is in orange, and another comparison data set, the EIA 923 monthly plant level production, which we aggregated to the to the balancing authority level following the infrastructure rollout, EIA 923 is in blue. The metrics that I'm going to provide, though, are with respect to the balancing authority reported production. Overall, this is a reasonable representation of the combined interannual variability and the evolving fleet. For the seasonal evaluation, in our example with BPA, we find a mean monthly relative difference of only 1%. Across all balancing authorities, we see a 9% overestimation, but this is largely due to overestimation in winter months and underestimation in summer months. In our future work, we're going to address this with further curation of observation data to disentangle any uncertainties across the whole process. Finally, on the right, the intraday hourly variability of our wind data is exceptionally well captured when comparing with the balancing authority's self-reported production. The Earth Movers Distance provides the difference in the units of the source time series. So for this application, it's going to be the megawatt hour difference in a day. But on the y-axis, this is in percent of capacity. So I've normalized this absolute difference by the installed capacity in that day to show the error in variability as a function of the installed capacity. So in this plot on the right, the EMD for each day is 1 dot. This is a box plot, and the median for wind is 0% for all these balancing authorities. The range on the y-axis is also quite small. For example, BPA ranges up to 0.03% for one of the days. This makes sense as BPA is a balancing authority with complex terrain. Next slide, please. Now let's turn to our evaluation of the solar historical hourly time series. Again, our simulated production in these two plots on the left is in orange. The balancing authority self-reported production is in green, and the monthly plant level production from EIA 923, which we aggregated to the balancing authority level, is in blue. Across all balancing authorities, we see a 7% overestimation of the average annual production. This is again unique to each balancing authority. So for example, in ERCOT, where solar production began in 2012, we have an 8% underestimation averaged annually. Overall, this is a reasonable representation of the combined interannual variability along with the evolving fleet infrastructure. Turning to the seasonal variability, for our example in ERCOT, the mean monthly relative difference is minus 15%. But across all balancing authorities, we have a 4% overestimation, which can be broken out as an overestimation in winter months and an underestimation in summer months. As with the wind data, we're going to incorporate additional observational data to address any uncertainties. For the intraday hourly variability for our solar power time series, we again have a very small difference between the balancing authority level observations and our simulations when normalized by the installed capacity in a given day. The capacity normalized EMD across balancing authorities, which report solar production, is less than 0.1%. We do see that for some balancing authorities, especially those in the Eastern Interconnect, such as ISO New England, the range can extend higher than 10%. But again, these data points are each for a single day. We think that the Earth mover's distance is a useful metric for evaluating the intraday hourly variability of simulated power time series, and that the EMD should be benchmarked with other data sets to address future steps in some regions. Next slide, please. So these data sets are published on Zenodo. We have produced these data sets for a 40-year baseline in capacity factor space, and these are provided in the link in above, and then in installed capacity space in the link at the bottom for use at the balancing authority level. Thank you.
I think at this time we are opening it for Q&A on this portion of the presentation, specifically on the development of the wind and solar data sets. We had one question on the chat that just got addressed with following those QR code on the wind and solar data set. I don't see any other question in the chat right now. So what about we move forward then, just to respect the time, and then please, any question that you may have, put them in the chat, and then Alison will be able to address them directly in the chat as well. Let's move forward. Thank you.
All right, can you go ahead 2 slides, please? Thanks. All right, so moving on to the energy drought section. When you think of drought, everyone thinks of hydrologic drought. Those happen on the scale of months to years. Energy droughts are conceptually similar, but happen on a much shorter time scale, from hours to days. And as we build out renewables on the grid, we only increase our chance of these weather-driven shortages in wind and solar. This is what an energy drought is. Next slide, please. So today, we're going to be focusing particularly on compound wind and solar energy droughts. So that's periods in which both wind and solar are simultaneously low. You can also look at periods in conjunction with high load, and this is really when the impacts happen for the grid. What we're really asking, since wind and solar are both weather dependent, we're really asking how certain aspects of the weather system co-vary over large regions, and those regions are balancing authorities. That's the region that is most relevant to the grid. What I'm showing here on the bottom right is to say that this is not a US-centric phenomenon. In Germany, they already have a name for periods of low wind and solar production. Those are called Dunkelflautes. Next slide, please. So building on the data that Alison just talked about, we had to pare things down a little bit to look at balancing authorities which had at least 5 wind and solar plants at utility scale within the BA. And just to be clear, we're not using the flavor of the data that Allison talked about that is scaled to the actual BA level production. So we have a 40-year historical record of basically weather years that is paired with 2020 infrastructure. So, and all those are from the EIA 2020. At the time, that was the latest that was available. I think now 2021 is available. But so once we have the balancing authorities specified and the plants picked out, we can aggregate the wind and solar to the balancing authority scale at an hourly time step. And then we pair that with load to create this complementary data set of wind, solar, and load for 40 years. Next slide, please. So what does that look like? Well, this is the climatological cycles of wind, solar, and load in different balancing authorities. And if you look closely, the climatological cycles are quite different depending on the regions that you look at. I've highlighted a couple in red on the first one in the middle. That's in Montana, where they have winter peaking loads. That happens to be when wind is high in that region, but when solar is low. And just another example in Pac East, that's in the Utah region. Load they have summer peaking loads there when wind is at its lowest and reasonably high solar. So this is all to say that the complementarity of these of the wind and solar with load is very different depending on where you look. Next slide, please. So how do we actually define these compound energy droughts? The first, and I would argue the most important step, is to determine the time scale that you're looking at. And by time scale, I mean a 1 hour time scale drought would be defined based on hourly data. That's that is the time step of our data. So that's the smallest we can go. You can aggregate the data up to larger time steps and look at larger time scales. So a daily drought would be a daily time step data. So we wanted to look at a range of time scales that are important for different applications. In particular, sub-daily time scales are important for grid reliability, for example. The next step is to build standardized indices. This step isn't strictly necessary, but it's very convenient for doing this analysis because what it does is it standardizes or normalizes the variables so that we can easily compare them across the different variables. So for renewable energy, that's called the standardized renewable energy production index. And for load, it's called the standardized residual load index. If you're familiar with hydrologic drought analysis, this is exactly the same as the standardized drought index in that field. The next step is to determine the threshold under which you would call it a drought. We opted to go with a dynamic threshold. The other choice would have been to do a fixed threshold over the whole time period. That the fixed threshold, for example, would tend to bring out droughts that happen when wind and solar were both climatologically low and load was high. If you do a dynamic threshold, you will also capture these events, but you can also get droughts that are abnormally high for a particular season, but may not be absolutely high. So we did this to capture a wider range of events. So once you have your indices determined and your time scale and your threshold, all you really have to do is pick out these coincident events when wind and solar are both below the 10th percentile at the same time. And if you're looking at high load, you just say when are wind and solar below the 10th percentile and the load is above the 90th percentile, for example. Next slide, please. All right, just an example of what this looks like graphically. What I'm showing here is a 2-month period from April 1987 to June 1987. This is using daily data, so it's a time step. It's a one day time scale. And you can see there's 3 droughts determined during this period. The first is on the left. You can see that the orange line is the solar, the blue line is the load, and the black line is the load, and the corresponding colored dashed lines are the thresholds. So you can see in this first example, the solar is below the threshold, the wind is below the threshold, and the load is above the threshold. So, and that happens for 2 time steps in a row. So that's a 2-day long drought at the daily time step. The next one over is a 6-day long drought under those same criteria. This is actually an exceptionally long drought. And then the wind pops up for 1 time step, and which breaks the drought, but then the drought continues. We're calling those separate events. For another drought happens for 2 more days. So hopefully that clears up how we're determining the droughts. Next slide, please. Okay, so stepping back for a moment from the compound droughts to look at non-compound droughts, just to give you some intuition about how long these droughts actually last. So I'm asked, so this is just solar for a moment, and I'm asking the question that what's the chance that a drought will last for 1 day or more? Well, the answer to that depends on the time scale that you're looking at. On the left, I have the hourly time scale, and if you look at these empirical cumulative distribution functions, on the left, your answer to that would be there's depending on the BA you're looking at, there's approximately 10 to 15% chance that a drought will last longer than 1 day. But if you look at the daily data, daily time scale, there's a 20 to 40% chance that a drought will last longer than 1 day. The reason for this is that the hourly time scale conditions are actually much more strict than the daily. We're on the hourly time scale, we're requiring every single hour to be below that threshold continuously. At the daily time scale, we only require that the total energy over that period be below the 10th percentile. So you could have particular hours popping up above the threshold as long as the total energy for that period is below. So your answer here would be about 20 to 40% chance of a drought longer than 1 day. Next slide, please. All right, so and just asking the same questions for wind, you can see the empirical distributions look a bit different, but the answers are similar here. What's the chance that a drought will last 1 day or more, a wind drought? Well, it's about 5 to 15% chance depending on the BA, and at the daily time scale, 20 to 30% chance. But note here that the wind droughts have a much longer tail, so those wind droughts do last longer overall, typically. Next slide, please. All right, so putting both of those things together, looking at now, these are compound droughts. When we look at only compound events, we can see that depending on the balancing authority in question, these hourly droughts, hourly timescale droughts can last from 16 to 37 hours, and the daily droughts can last 3 to 6 days at the most. Next slide, please. All right, so now looking at both frequency and duration of these events. On the left, we have the hourly, and the right, we have the daily time scale. The size of the dot represents the frequency of the events. So the average number of drought events per year through our 40-year period. And the color represents the maximum, the longest drought we observed over that 40-year period. And the way you would read this, focusing on California for a minute, California has approximately 10 compound droughts a year on average that last up to 18 hours. That's how you could read this. And then on the right, on the daily time scale, California has approximately 4 compound droughts a year on average that last up to 6 days. So the reason I'm highlighting California here is to hopefully make the point that the answer to these questions about duration and frequency really strongly depends on the time scale. So if you look at California, for example, on the hourly time scale, the maximum duration event falls in the smallest bin. So it has some of the shortest duration events of all the balancing authorities we looked at the hourly time scale. But if you look at California, which is CAISO, on the right, it actually falls in the highest bin on that graphic. So up to 6 days, J-long droughts. So the characteristics and the inter-BA, the spatial relationships do change quite a bit depending on the time scale that you're looking at. And then one last point here is that you'll notice that as we increase the duration, the frequency of events goes down and the duration goes up. That is a very consistent result across all time scales. Next slide, please. Okay, the final piece of this drought analysis is the magnitude. We looked at frequency and duration, now magnitude. There's several ways to assess the magnitude of an energy drought. One way is we have this 10th percentile threshold, and you, for a particular drought event, you can look at what is the total energy deficit below that threshold. That is one measurement of the magnitude of a drought. And that's what I'm showing here across all the BAs in green for just wind and solar droughts. So you can see for just wind and solar droughts, these events can last from perhaps 0 to 10% in some cases of the peak load. Sorry, and I'm showing that deficit as a fraction of the peak load. I apologize. Then if we look at those wind and solar droughts, only those occurring during the high load events, we actually see that it's not apparent based on this graph, but the frequency of those events goes down by a lot, but the magnitude goes up on average to approximately up to 10 to 15% of the peak load. So wind and solar droughts in conjunction with high load are less frequent, but more severe on average. Next slide, please. All right, I want to shift gears a little bit to talk about one of the primary applications of energy droughts, and that is to battery storage. So there are two main classes of battery storage in operation right now. Those are the short durations ones that are 1 to 2 hours. Those are a primary application to grid stability and reserves, that type of thing. Then you have the longer duration batteries, which are useful for load shifting in particular and storage management, such as charge and recharge cycles. Now, there's a lot of new storage planned in the next few years, battery storage. And the EIA estimates that 60% of this new battery storage is intended to be hybridized with wind and solar plants. So this is perfectly positioned to mitigate energy droughts. Next slide, please. All right, so what I'm showing here is the frequency of droughts, so the number of droughts per year that happen of wind and solar compound droughts that happen during periods of high load, and it's broken out by balancing authority. So just thinking of battery storage here, that the duration of existing battery storage and maybe incremental improvements in that technology are well positioned to mitigate these 1 to perhaps 12-hour time scale droughts. But we really are observing droughts happening on much longer time scales for much longer durations, which existing battery storage is not adequate to mitigate. So this really points to technological and market gaps that we see needing to be filled in the future. Next slide, please. So just wrapping up this energy drought section with some takeaways, and then we'll do a quick Q&A. These compound energy droughts that I've been discussing, I hope I made the point that these vary quite a bit across spatial and temporal scales. These present some unique regional challenges in order to mitigate them. In our 40-year record, the longest energy droughts we observed at the hourly time scale lasted from 16 to 37 continuous hours, while at the daily time scale, we saw them lasting up to 6 days. And then when you look at wind and solar droughts that occur during high load periods, these events are much less frequent, but more severe on average. And just a plug for the data sets, these are all available online. The first one, Allison already mentioned, this is the 40-year period historical wind and solar. And then the actual energy drought data that went into this analysis is also available, as well as the preprint for this work. And I think I'm going to pass it to Natalie for a quick Q&A. Next slide, please.
So we just had a very quick question that I think, Carmen, it would be great to really clarify for the audience. The first one is, could you remind exactly how you developed that dynamic threshold and how this threshold clarify the science question that we are after?
Yeah, that's a good question. I didn't go into a ton of detail, but we developed the dynamic threshold based on the week of the year and the hour of the day, if we're talking about a sub-daily timescale, because you have these, the diurnal cycle of solar, so you need to incorporate the hour of the day. By doing this dynamic threshold, we're able to capture events that are seasonally abnormal, as well as the ones that you would think about happening in the low period, the climatologically low season. So we're building a richer data set than you would get from just a fixed threshold, but that isn't to say that a fixed threshold might not be useful for a particular application. That definitely could be useful there. Okay.
A quick question also on, do we have enough data to establish reliable drought threshold, especially here we're getting at the 90th percentile?
Yeah, so it is, the threshold itself is a bit arbitrary. I would say that 40 years is a reasonably sized record, but we did do some sensitivity analysis with the threshold itself. That's available in the paper. But it goes kind of as you would expect. But yeah, the threshold itself might need to be changed depending on the application and how extreme of events you're looking at. But yeah, the last point is that when the threshold goes, when you get more extreme, you get less events. So you do need more data to capture those higher thresholds.
And as we build the infrastructure, and then there will be new data sets that are specific to that infrastructure, how this definition of threshold change? Do you keep it at 10%? Is it 10% of historical? Can you tell a bit more about how those thresholds are they dynamic as well, or are they static?
Yeah, that's a good point. The 10%, the threshold is based on the historical data. So if you wanted a different threshold that was maybe based on some future information, that is certainly something you could do. It's kind of plug and play with whatever threshold value you want to choose, depending on your application. Yeah, that's what I'll say there.
Perfect. There are a couple of other questions that we'll be able to address in the chat or further at the end of the presentation. So let's move forward, as we are now going to dig into the application and how we use them. Go ahead, Cameron.
Next slide, please. And I think this will be Casey.
Yep. Thanks, Natalie, and thanks, Cameron. So Cameron closed out his portion of the talk by talking about one application of this data set, looking at energy storage requirements. I'm going to talk about two more things that we've been working on as part of GODEEEP, where we're trying to get the data sets in use in industry and in near real time. So the first application is these two WEC working groups that we've been contributing to. The purpose of these working groups is to assess the reliability of the projected Western US grid on 10 and 20-year horizons under extreme cold and extreme heat conditions. So we were able to adapt and leverage the load, wind, and solar data sets that you've been hearing about, as well as the underlying meteorology data set, to answer a series of questions for these working groups. So I'll go through each of these three questions in turn, starting with looking at typical durations for heat waves and cold snaps. Next slide, please. So Allison and Cameron both mentioned the underlying TGW dataset, which contains 40 years of historical data across the entire United States. We have a post-process version of that where we aggregated the meteorology by balancing authority. And we were able to use that time series of meteorology by balancing authority to look at the hottest and coldest day of each year over that 40-year historical period for all the BAs in the WEC. So what I'm showing here are time series of temperature evolution composited around the hottest day of the year in the top panel and the coldest day of the year in the bottom panel. So in the center of the x-axis there at T0, that is the day of the hottest temperature of the year. And then you're looking at a time series from 2 weeks before that event to 2 weeks after that event. So the light red curves here are each individual year in the data set, and the black is the composite or average over all 40 years of the data set. And you can see some extreme events in here, like the 2019 Los Angeles heat wave that I've highlighted in red up here on the top. That comes up later on in my talk. So we can use this analysis to characterize what is a typical heat wave in cold snap. And you can see from the plot that they last on average about 6 to 7 days and are symmetric about the maximum or minimum temperature day. What that means is, if you were trying to assess grid reliability, you need to look at a full week period because that tends to be the temporal extent of these events. I'm showing the example here for just one balancing authority, Los Angeles Department of Water and Power. We did this for all the balancing authorities in the WEC, and the results are roughly consistent. So we use this data to actually find particular event dates to study extreme hot and cold events. Next slide, please. So the next part of our analysis wanted to understand the spatial structure of these events. So when extreme heat or extreme cold was impacting the Western US, what did that look like from a meteorological perspective? So I'm showing here 4 temperature maps for the 4 highest historical winter loads over the 40-year historical period. So we took the meteorology and ran it through our load model that we discussed in the first deep dive, and then picked out the 4 highest historical winter loads to look at the weather variability here. And just note that because load naturally grows over time, the loads are normalized in order to be able to compare consistently across the entire data set. So if you look at these maps, the things that are consistent are the cold snaps, the extreme cold and resulting high loads tend to be focused in the Pacific Northwest, with the most extreme colds extending eastward into the Dakotas. You don't really see extreme cold values extending into Southern California or Arizona. The other thing the meteorologist in me is excited about is the signal of the cold front is quite obvious in 3 out of the 4 plots. So these are all post-cold frontal events, with the exception of the one on the bottom right. All right, next slide, please. We repeated the same analysis, but looking at the 4 highest historical summer loads. And from this, we can discern that the heat waves impacting the Western US are spatially broader, right? You have high temperatures that are hottest in the desert Southwest down in Arizona and Southern California, but you also see extreme heat extending through the Pacific Northwest and all the way into the Midwest and Texas, right? This means that heat waves impacting the West tend to be spatially broader than the cold snap events. And this has implications for how you might, for example, design a transmission system that could alleviate stress during these events. Next slide, please. So once we've sort of identified these events and characterized their meteorology, the next thing that we wanted to ask was, how does the wind and solar generation potential vary during these heat wave and cold snap periods? So what I'm showing here are time series, composite time series for 9 balancing authorities in the West, starting with Bonneville Power in the upper left and moving so on and so forth. And what you're looking at is the evolution of the wind capacity factor composited on the days since the extreme temperature. So in this case, we're looking at heat waves. So day 0 here is the peak of the heat wave, and then you're looking for 3 to 4 days on either side of the peak of the heat wave. The lines, the solid black line, the heavy black line shows the mean wind capacity factor composited over all 40 years of the historical data set. And then the lighter dash line, or the lighter lines, show the 10th and 90th percentiles of the distribution. So from this, what we can say is that balancing authorities in the Pacific Northwest tend to show a notable suppression of wind generation capacity during these extreme heat events. And we've highlighted 3 balancing authorities in red here where that signal is quite obvious. The signal in the other BAs is a bit more muddy. and there's no clear discernible signals in the wind generation capacity during heat wave events. We also looked at this for cold snap events. In the next slide, if you'll advance, we look at the solar generation potential, and here we're switching from heat waves to cold snaps. Next slide, please. There we go. So it's the same plotting convention, but in this case, we're compositing on days since the extreme cold event. So the signal here is a bit more robust across balancing authority. And what we can see is that solar generation tends to be lower before and after the extreme cold snap period. So you get this sort of inverted U shape with highest solar generation capacity on the day of the most extreme cold and lower values before and after the coldest day. And the other thing that you can see is that you do get you tend to have higher overall production during these cold snap periods, and we think that's due to lower panel derating due to the temperature derating effect. So we have this analysis for heat waves as well, and we'd be happy to chat about that offline if you like. Next slide, please. The final thing that we did with these WEC working groups was try and help them select a specific heat wave to study in detail. After some back and forth, we ended up landing on this July 2018 heat wave event where you see temperatures in inland California and Arizona exceeding like 112 degrees Fahrenheit, quite hot. So next slide, please. So once we identify the event, we can look at or characterize the variation of wind and solar potential during this particular event. So the plots I'm showing here are for a single balancing authority, California ISO, and the plots on the left show the entire year, so the entire 2018 weather year, the solar capacity factor, and then the area in the green is that extreme event that we want to focus in on, that heat wave, which is shown in the time series on the right. So we can look at this both, the variation during that peak week of the heat event and the solar capacity factor. We can also use our forward-looking TGW data set to look at that same event in the future context under climate change. So that's what's shown in the bottom panel in red. And you notice that the solar capacity factors are slightly lower due to the higher temperatures in the future under climate change. Okay, so that summarizes our work for the WEC. I'll close out, if you go one more slide, by talking about some work that we've done with the National Transmission Planning Project. I know many of you are also involved in NTP. So the purpose of that project is to explore how increased transmission can potentially alleviate grid stress during extreme events such as heat waves. So our contribution to this study was to create hourly time series of load, wind, and solar based on the 2015 and 2018 weather years that can be used as input to the GridView production cost model in order to study like resource adequacy and grid stress under these extreme events. So I'll note that because NTP is using a projected system out to 2035, our winds, load, and solar values are scaled so that they may match the baseline system projection for 2035 for NTP. So one more slide, please. So what I'm showing here are time series of the total load summed over all the balancing authorities in the WEC. The top panel is the original loads that NTP was using that are coming out of GridView for their base case, and then the bottom is the loads that we produce based on the GODEEEP extreme event analysis, and this is based on the 2018 weather year. So by putting the 2018 weather year into this model, you can see these consecutive heat waves occurring in the summer, including that extreme event in July of 2018 impacting Southern California. I would say that these loads, they sum to the same annual energy values, meaning that they're scaled to the same annual energy values. But the idea is that by putting these heat waves in there, you can assess the system reliability and performance under these extreme heat conditions, including exploring the impact of increased transmission availability. Okay, so with that, I'm going to pass it back to Cameron to close us out before we get to Q&A.
All right, next slide, please. All right, just talking about where we're going to take this work in the next few months, and this work is already well underway. We have these the TGW simulations, which incorporate multiple climate projections. And we're pairing these with decarbonization scenarios. You already saw some of these results in Deep Dive 2. And these feed into future plant sightings. And also you heard about that in Deep Dive 2. And all of this is going to feed into analysis that is underway on future energy droughts and extreme events with a particular eye towards grid impacts and storage needs. And we're doing these projections all the way out to 2050. Next slide, please. All right, so all of the code and data that we talked about today is publicly available. It's all listed here. Not expecting you to write all this down right now, but the slides will be published and this webinar itself is being recorded. So, and all of this will be available shortly after the webinar. We'll also feel free also to reach out to anyone involved in the webinar, and we'd be happy to give you these resources. Next slide, please. All right, just some final takeaways from this webinar. The cornerstone of all of this work is the wind and solar data sets using consistent, which were consistent with existing infrastructure. Allison showed some evaluation against BA reported power. And the first application of this was to energy droughts, these compound energy droughts across the United States using these standardized definitions. But these wind, solar, and load data sets together are very flexible and are actively being used for other studies. Tacey talked about the first two applications to NTP and WEC, and another one we did not mention, which is for NERM reliability studies. Where we're going to be taking this work in the next few months is looking at evolving infrastructure and climate under decarbonization scenarios, and one we didn't mention, which is seasonal, longer timescale droughts, which necessarily incorporates hydro, as well as some future applications to storage technologies and market development. And I just want to mention that we're actively looking for any feedback, so we welcome any further discussions that come out of this. I will pass it now to Natalie for the Q&A.
And actually, before we go into the Q&A, if you go to the next slide, so we had a great presentation. And I just want to make sure that we promote our next webinar. This is going to be a Deep Dive 4, which is also going to be our last deep dive of this GODEEEP series. And the focus is going to be on evaluating the impact of decarbonization on disadvantaged communities. Please register, plan in advance, and there are multiple angles to this research on understanding not only the impact on disadvantaged communities, but also how to work with the industry to ensure that your integrated resource planning or all of this future infrastructure, what are the infrastructure that have the most chance of succeeding and being adopted by the communities. So please chime in. Again, go to PNNL. Okay, you have the link here. You also can find all the links on www.godep.pnl.gov. So maybe we can go to the next slide and now address some of the great questions. We were able to address a number of questions that were on the chat. Please start bringing them in. There is a question that we got earlier that we didn't get to, was for Cameron and maybe also Casey. We had those discussions on the energy droughts. We've had those discussions on the thresholds, seasonal versus short-term to address storage. What is the guideline for the industry to determine what timescale to be used in practice, since the conclusions on energy droughts are so different?
Well, I think like you may have already mentioned, it really depends on the application. So I think it would be sort of the characteristic time scale of the application you're looking at. For reliability, you would almost certainly want to look at hourly time scale. For things like droughts which correspond with other resources, maybe like hydro, you might want to look at longer timescales up to the daily or multi-day events. So it really is application specific.
Excellent. Can you tell us a little bit more, like we're going back to much earlier in the webinar when the team explained a little bit about how the wind and solar data sets were developed, and you mentioned that there was a bias correction performed. Okay, can you tell us more about the process and what did that bias correction, how did you see that we needed it and what was done?
Sure. Yeah, the bias correction was, we just were doing some basic validation against observationally based data sets, particularly NSRDB, and we saw a bias there, which keyed us off to probably a need for bias correction. Now, the bias is mostly in the solar radiation, which we think is probably due to the representation of clouds in the model. But we chose to bias correct on the final step on the power itself, because that can perhaps there's some other biases due to the use of the disk model, or anyway, that will capture all the biases in the whole process and correct for them mostly. But this was done using just a simple quantile mapping approach using historical NSRDB data.
Excellent. We did address the impact of using a dynamic threshold. Did you consider energy drought that span multiple balancing authorities?
Oh, that's a really good question. No, we haven't, but that's a really nice extension. I would call something a drought that span multiple balancing authorities, maybe a regional drought, something like that, and that would definitely be a really interesting extension to look at with these energy droughts.
Okay. Can you talk why it's necessary? I think we're going to go more in the load and the heat waves there. Can you talk a bit why it's necessary to scale the loads for different system projections like you showed for the NTP project?
Yeah, that's a good question. So I think it's important because these projects are building system projections based on a certain set of assumptions about how the load will grow or how the generation capacity will grow over time. So in GODEEP, we talked in Deep Dive 1 that our projections are based on GCAM USA's decarbonization scenarios for the United States, and there is a 2035 time point in that. But we've naturally made a different set of assumptions than what the NTP project is making about how load and generation will grow over time. But because our approach is relatively flexible, it's easy to rescale our load projections so that we have the same total annual energy consumption that their system was designed for, so that you're comparing apples to apples when you actually try and stress the system.
All right, gonna go to more of the question. So a lot of the here we really those wind and solar data sets are really part of GODEEP for some of the questions. There are a couple of other wind and solar time series data sets that are out there. So it's not maybe being a little bit confusing about when to use, when should we use GODEEP wind and solar data sets compared to others. Can you provide a little bit of clarification of what those GODEEP wind and solar time series bring to the community and when they should be used? I think that would be for Alison, you're muted.
Can you hear me now?
Yep.
Great, thanks. Yeah, I'll take this one. So yeah, these renewable power time series that we developed were created using specific power plant configurations. And this is the first data set that is using that. Most existing data sets out there right now use default characteristics, but this is a data set of individual unique characteristics to every single power plant in the United States. In addition to that, these data sets cover a longer baseline than that which is otherwise available. So currently it covers 40 years of historical data. And in addition to that, one of the most powerful components of this data set is that it's based on a meteorological simulation that provides the weather inputs to both wind and solar. So they're coincident across all the variables.
And can you just threading on this, because I think that was also in some of the takeaways. There are some wind and solars, and what is the recommendations for the community at this time for the one choosing the data sets, but also the one developing data sets? What did we learn?
So these data sets should be used at the balancing authority level. And for developing data sets, it's definitely going to be more important for studies to develop the data sets with specific plant characteristics. Yeah.
And I think also the metrics. I think that developing a benchmark, I think like the team says, this is one of the first benchmark that are available with all of the metrics. And so that will be a great feedback that we rely on with respect to the community, is making sure that we have more discussions on the metrics and we share all of those metrics. So that's perfect. I have another question that is, do we have capacity expansion for wind and solar to meet higher decarbonization goal beyond the 10-year ADS case in WEC? So I think that has to do, maybe we can talk a little bit more about how we've been working with the WEC. They have their 2032 case, so the 10-year out, but they've also been working on their 20-year out. Casey and Cameron, do you want to address if how the wind and solar data sets have been developed for those for the 20-year out?
Yeah, I'll take a stab at that. So yes, the answer is we have two different scenarios. We have the business as usual and the net zero capacity expansion, where we're using the 2020 sort of the historical existing plants, and then we add, depending on as we move through the process of every 5 years, we build out the infrastructure more and more based on these two scenarios, and we add that in to the wind and solar data set. So as we move out to the 2045, we have more and more wind and solar capacity on the grid.
Casey, did you want to complement?
No, I don't have anything to add.
Okay. So like Cameron said, and that's going to be pretty important, the fact that the wind and solar, it's a huge computational resources. The fact that this is gridded allows to have the different partners here. If you want to test a different infrastructure that is not the one that we develop with our model, this is the point of the entire GODEEEP platform, is to be flexible. So at each point of the resource adequacy, from the infrastructure that we build or infrastructure that you build, is to have access to those wind and solar data sets that fits your infrastructure. Some of the questions that are going to be brought forward was also the plant configuration. For the historical evaluation, we use the EIA configuration. Moving forward, there are places where we do a bit more assumptions on what the plants are going to look like. And that's also something where we're making some assumptions, but we would really benefit also from feedbacks from the industry on any spatial and temporal variability on this configuration moving forward. I do not see other question at this time. But I really that we had a fair number of questions, so that was extremely exciting. Can really say thank you to the speakers for this brilliant presentation. I'd like to also really thank the audience for all of your great questions. As I mentioned, the webinars and the deep dive our success is based on your questions and your feedback. So please write to the authors, Cameron, Allison, and Casey here. Visit the godeep.pnnl.gov, and that's 2N. And please provide those feedbacks, and hopefully we can get back to you. With this, I think that we'll try to give you 15 minutes back to your day. And thank you again so much for attending our GODEEEP seminars, and see you in 2 weeks for Deep Dive 4. And we're going to close the webinars. Thank you.